Guido's code and ported that to Raspberry Pi Pico. Raspberry Pi Pico means you have 500 kilosamples per second ADC, which is very fast, which is faster than we need. And it has all the capabilities, enough pins, and it's cheap as an Arduino or Atmel 328, which is very expensive nowadays. So we started reading Arjante's code, his design. Of course, his design was similar to the QCX design and Guido's approach, except instead of doing the SSP generation over an 5351, it was using an FST, another FST to do the IQ modulation. So top side is the IQ demodulation, the bottom side, blue side, is the IQ modulation. So fast ADCs, so you can sample the frequency. Arjante didn't, but then I will show Klaus did it, and he sampled 160 kilohertz of frequency bandwidth, so you can see roughly 100 kilohertz bandwidth on a spectrum waterfall, which is good. Also consists without ideas. So, and also here, he used the approach to use the PWM channels to generate the IQ modulation. Then I can say, what I can say, yeah, it has very fast. You see, he also implemented a waterfall and the oscilloscope on the device, because Pico RP2040 is really a powerful MCU compared to the Atmel one, 8-bit one. It's a very powerful MCU, so you can do a lot of things. And at the end, you have a lot of space on the MCU that you can develop extra features on the device. So we decided to move to this platform, to Raspberry Pi platform. And thanks to Papa Yankee to KLA. I think he's not here, but up-down converting or not? As I said, the original idea was to up-convert, down-convert. It has its own problems, benefits, but makes everything a little bit more complex. So when we go to the schematics, we have a down converter, then we have a toll detector, then we have the IQ signal. Is there a way to connect all these together and have a single module there to directly input the RF and have the IQ out? Yes, those are the IQ modulators and the IQ demodulators in the market. You can easily go to, for example, to analog devices side and select whatever you want. It does similar thing with the other circuitry, so it's all in one chip, easy to use. Then it makes the whole design a little bit more simpler. Yep. Simpler, I mean the IQ demodulator, the IQ modulator, the MCU, a display control, microphone sampling, and this is wrong, this is PWM speaker. And the final device should look like something this. And if you dive into an IQ demodulator, you see similar blocks as you do for an SDR IQ demodulation using a toll detector or a mixer. Then we choose analog devices 8348. Why? One, it's cheap. I think it's under 10 euros. It does everything for you. It works from 50 megahertz to 1 gigahertz, which is enough for this QO100 experiment, which we were planning to work on 739 megahertz, which is the output of the LMB. But also it has pin compatible parts, I think 8347, not sure fully, but which can go beyond 1 gigahertz up to 2.7 gigahertz. So just changing the chip, we can have some other frequencies possible for us to use. It has an integrated VGA, so 45 dB is a lot. If you think that the output of an LMB is around 60, 70, 80 dBms, then 45 is a lot, you are very close to retransmitting that signal back. So it's good to have that, and you can feed any ADC with that signal without amplifying. Of course, we will amplify and filter it, but even you can use the IQ signal directly in the MCU. Bandwidth is too much, 75 megahertz, that is too much for an SSP communication. So we use some filters that I will show in the schematics how we do it. We cut the bandwidth down to a place that we can use, let's say we need only 100 kilohertz of bandwidth because we cannot sample more than 100 kilohertz. So we did that. What else? The local oscillator drive is very low, minus 10 dBm. Most of the PLLs and synthesizers can drive this. Of course, from analog devices, it's easier. And the voltage range is very good. Same story for the transmitting part. Why we used these parts for, it's a part of reverse engineering. Maybe you heard about this Etus Research, USRP, Etus Research, USRP SDR. I had the boards on that and I was just looking, hey, what they are using, and I saw that, hey, they are using 83, 46, and 48. Hey, I was planning to use those. If they used it, and if they sell it bloody expensive, then these are something good. So I can use it. I know the chips are cheap. Chips are cheap. But they do what they need to do. So we decided to go with these ones. And for this one, for example, for 46, it's easy to solder because it's a TSOP layout, and it has compatible 45 and 49, which can go to 1 gigahertz or 2.7 gigahertz just by replacing the IC. What else can I say? Yeah, DC to 70 megahertz, more than we need. And the output power is minus 3 dBm, which is a huge power. You can drive any power amplifier you need. So even the output of this can drive the amplifiers. What else? Yeah, nothing important. Of course, it requires only minus 10 dBm of local oscillator. Where we failed. This part is where we failed. Yeah, the original device that I implemented and I did QSOs was this one. This is the microphone, and this is the PTT. And the output was driving an amplifier of 2 watts, and I was able to communicate Q100 with this one. It's easy because this is an AD4351 frequency synthesizer that you can go down to 2.5 kilohertz steps only using the original crystal. But it was enough, so you can just get close to the frequency. You call there, people just tune on you. You don't need to tune to everybody. So I tested this, the modulators and demodulators on this board. So they will be here if you want to see, but okay, last designs are similar. Then we decided to change the ADF 4351 to something else. We started searching. Of course, manufacturing was another story. Maybe you can.
Yeah, we started. Yeah, you finished out.
Yeah. We thought that we can use some analog devices, PLL VCOs for this, and I just picked up 4360 because it has very different variations that those are pin compatible and can work with our different bands for us. Plus, it was on JLC PCB manufacturer. So we don't need to solder these components by hand. We thought that they can solder those to the PCB for us and it will be easy. It didn't run that way. With this one, the lowest step frequency we were able to achieve was not good because it was an integer PLL VCO. We said, okay, we can solve this, and the problem, it's a software-defined radio. I don't need to get the exact frequency. I can tune to a frequency and listen to the rest. Yes, it worked, but it put a lot of complicacy to the device. It became complicated, the software part. You need to handle that, you need to shift the frequency, you need to take care of the edges, etc. But in this version it's working like that because we didn't have time to replace this with any other frequency synthesizer. But when we saw that this is not the ideal because we can find some other frequency generators like the HMC 830, which is a heated microwaves component, but both by analog devices, I believe to be killed, because I didn't find any support about this device. Those software, all the softwares are for old Windows 2000 and those kind of things. It's not easy to develop something with that one. I bought those kits from the net, which are ready, so I can try and generate a frequency, because with that one you can go down to 1 hertz step size. So 1 hertz is much more than I need. So 10 hertz, 100 hertz is enough for us. But it worked. Everything in the software worked except the frequency generation. It didn't generate the frequency. It worked. I was able to communicate with it, set the registers, everything, but it didn't work. So we decided not to use that one. So this is an open topic to be discussed in the future. So what to use there, which fractional PLL VCO we can use there, which is the easiest way for people to solder it themselves, not this kind, but maybe a T-SOP alternate for that. We just changed our mind about this, what was it, a month ago?
A month ago.
So we didn't have time to switch it with something else, but here you will see this version working on the devices. And of course it was important that while Bart was designing the PCB, he was telling me, hey, I found this component on GLC PCB's repository. Can we use this? Can we use that? So GLC PCB having that in their repository was another reason to use this one, not another one.
Alright, this is the design of the PCB. So how we started is, first we decided to do through hole for a gigahertz rig, not a good idea. So at the end, I considered the time, and the time was in essence, so I went to all assembly components, as you can see here. And we wanted a modular approach because I was going to produce the PCBs and send it to him. He has to test it, get the software running on it, and I have to continue because it's a process. So what I did was, first, let me show it like that. This is the right, yes. This is the transmitter side. So the other side, right? Yeah, sorry. Yeah, the other side is the transmitter side. What we did was, we wanted to, maybe you guys know me, I like stacking PCBs on top of each other a lot. So stacking and making a modular approach. So the first one was the transmitter. You can see there. But the problem with the transmitter was, now we didn't have the receiver, we have to develop it independently. To do that, I designed a kind of a LCD display keyboard hat on it. So we got it done in GLC PCB, they're pretty good. I mean, they did it in like a week or so, right? And sent it to us. And then I sent it to Boris, and Boris started to work on it while I was working on the receiver RX side. Now everything is coming on top of each other. So the bottom one will be the kind of a PA PCB, which holds the power supply also, which is, we don't have it here, but we can show it there. And then on top we have the transmitter, on top we have the receiver, and this is the final control board. This board controls actually independently the transmitter and the receiver, but there's a sync button also, which syncs the same frequency with all the shifts and etc. to both, so you can operate full duplex or as a simplex transceiver. One more anecdote here. I never designed a 2.4 gigahertz PCB. My limit is 30 megahertz, which is easy. So when he gave me the task, I showed, how am I going to do that? Because if you move a line a bit longer or so, it becomes a capacitance or inductance. So what I did was, he sent me a professional board. I got the board enlarged in an A4 and then to an A3 and measured in scale what they used, and then shrinked it and put it on the PCB, and it worked like a charm.